Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of object-oriented software engineering. We'll dive into key concepts like introduction to UML, notations, relationships, stereotypes. Let's get started. Slide 1. Introduction to UML, Unified Modeling Language. Let's start with what UML is. UML stands for Unified Modeling Language, and as the name suggests, it's a standard modeling language used to design and represent software systems visually. Unlike textual descriptions, UML allows us to use diagrams to model software architecture, design, and functionality. It is especially useful in object-oriented software development because it models real-world entities as objects with relationships and behaviors. Now, why do we need UML? Imagine designing a complex system without visual representation. It would be extremely difficult to understand and manage. UML provides a clear and standardized way to document systems, making it easier for developers and stakeholders to communicate. An example is a class diagram where we show classes like customer and order and how they interact. Another important point is that UML is independent of programming languages. Whether you are using Java, Python, or C++, UML focuses on design, not code. So, in summary, UML helps us visualize, design, and communicate software systems efficiently and reduces misunderstandings during development. Slide 2. UML notations, symbols and their purpose. Moving on to UML notations, which are symbols used to represent different elements of the system. First is the class notation. It's a rectangle divided into three sections: the class name, attributes, and methods. For example, a class, employee, may have attributes like name and ID, and methods like calculate salary. Object notation represents a specific instance of a class, like an individual employee. It looks like a rectangle but the name is underlined. Use case notation is an oval that represents system functionality, like login or place order. Actor notation, shown as a stick figure, represents users or other systems interacting with our system. For example, a customer or admin. Interface notation, represented as a circle with a line, shows what functionality a class promises to provide. Package notation looks like a folder and is used to group related classes or diagrams to organize the design. Activity notation is for modeling workflows or processes, like the steps involved in placing an order. State notation shows various states of an object. For example, an order could be pending, shipped, or delivered. So, notations help us represent complex software components clearly and understandably. Slide 3. UML relationships, types and meaning. Next, let's talk about UML relationships, which define how different elements of a system interact. The first is association, which shows a basic relationship between classes. For example, a teacher teaches a student. Aggregation is a special type of association where one class contains other classes, but the contained classes can exist independently. For example, a library contains books, but books can exist without the library. Composition is a stronger relationship. If the whole is destroyed, parts are destroyed too. For example, a house contains rooms. If the house is demolished, rooms don't exist. Generalization or inheritance shows that one class is a specialized version of another. For example, a dog is a type of animal. Dependency is a temporary relationship, where one class depends on another to perform a task. For example, a customer might use a payment service. Realization shows that a class implements an interface. For example, printer implements a printable. Multiplicity tells how many objects are involved. For instance, one order can have multiple items represented as one. Navigability shows the direction of the relationship, meaning which class knows about which other class. Understanding these relationships helps model the structure and interactions of the software system. Slide 4. UML Stereotypes, Concept and Purpose. Now let's understand UML stereotypes, which are custom labels added to UML elements to provide additional meaning. They are shown in double angular brackets, like less than interface greater than. Stereotypes help extend standard UML symbols to suit specific needs. For example, less than interface greater than defines an interface in a class diagram. Another common stereotype is less than entity greater than, representing classes that hold data, such as student or product. Less than boundary greater than represents system boundaries, often the user interface, like a login form. Less than control greater than represents control logic, classes that manage operations and workflows, like order manager. Less than exception greater than represents classes or elements handling errors. Less than abstract greater than shows an abstract class, which cannot be directly instantiated. So, stereotypes help to clarify roles of different classes and components, making diagrams more meaningful and understandable. Slide 5. Advantages of using UML in software engineering. Let's now explore some advantages of UML. 1. Standardization. UML provides a common way of representing software designs that all team members can understand. 2. Visualization. Complex software can be visually broken down into diagrams, making understanding easier. 3. Improves communication. UML serves as a shared language among developers, designers, and clients, reducing communication gaps. 4. Simplifies complexity. Large systems are split into manageable diagrams for analysis and design. 5. Early error detection. Design flaws can be identified and corrected early, preventing costly fixes later. 6. Supports object-oriented concepts. Naturally aligns with object-oriented principles, making design efficient. 7. Reusability. Encourages reuse of design patterns and components across multiple projects. 8. Documentation. Serves as official documentation for system design, useful for future maintenance. 9. Tool support. Many tools like Stereotypes or Rational Rows support UML, enabling automatic diagram creation and validation. These advantages show that UML is a powerful tool for effective software design and development. Slide 6. Differences between UML relationships: association, aggregation, composition, dependency. Now, let's understand the differences between four important UML relationships: association, aggregation, composition, and dependency. These relationships define how objects and classes are connected or interact with each other in a system design. 1. Association. Association represents a general relationship or connection between two classes. It shows that objects of one class can be connected or linked to objects of another class, but there is no ownership involved. For example, a teacher and student. A teacher teaches many students, but neither owns the other. It is simply a way to show interaction. 2. Aggregation. Aggregation is a special type of association that shows a whole-part relationship where the part can exist independently of the whole. For example, a library contains books, but even if the library is closed, books can still exist elsewhere. This represents a shared ownership, and it is weaker than composition. 3. Composition. Composition is a strong form of aggregation. It also shows a whole-part relationship, but here, the part cannot exist without the whole. For example, a house contains rooms. If the house is destroyed, the rooms cease to exist. So, composition represents exclusive ownership, and the part's life is tightly bound to the whole. 4. Dependency. Dependency represents a temporary relationship where one class depends on another class to perform a function. It means if one class changes, it may affect the other. For example, a customer depends on a payment service to process payments. The relationship is short-term, just for that action. 5. Lifespan of parts. In association, there's no effect on the lifespan of either class. In aggregation, parts can outlive the whole, meaning if the whole is destroyed, parts may still exist. In composition, if the whole is destroyed, the parts are destroyed too. In dependency, there's no sharing of lifespan, just temporary interaction. 6. Type of relationship. Association, aggregation, and composition are structural relationships, showing how objects are connected in a system. Dependency is a functional or usage relationship, showing one object uses another temporarily. 7. Strength of relationship. Association is a basic link, showing interaction without strong ties. Aggregation is stronger, showing a meaningful whole-part connection but with independence. Composition is the strongest, enforcing that parts cannot exist without the whole. Dependency is the weakest, showing just a temporary need. So, in summary, these relationships help us design real-world connections in software, and knowing their differences allows us to model accurate, logical relationships based on how components should behave together.